Hello everyone, welcome to today's webinar and those joining from US, happy 4th of July. I'm Abdullah, leading camera team at 10x Engineers, and let me briefly introduce what we do at 10x Engineers. So we are hardware design and verification services company, focusing on RISC-V image signal processors. And for the image signal processing part, we develop imaging algorithms from the algorithm development to their RTL implementation and their FPGA implementation, and then also evaluating their quality and then improving those algorithms. So we are excited to have Uwe with us, CTO Image Engineering, as our host speaker. So Uwe actually is a leading authority in the field of image quality testing, and he has extensive experience in developing and implementing standards and technologies for various industries, including automotive, mobile phones, etc. So under Uwe's guidance, image engineering has become a global leader in the image quality, test equipment, manufacturing, and methodologies. So recently, he has significantly contributed into the IEEE P2020 standard, which is a standard for developing image quality for the automotive domain. He's an active member of the AutoSense Academy, where he shares his knowledge on automotive cameras, focusing on the importance of calibration, characterization for enhancing the camera performance. So, Uwe, we are excited to have you with us today to share your insights and expertise. So, over to you.
Thanks, Abdullah. Very kind introduction, and thank you. So welcome everyone. I was invited to talk here, get the chance to talk to you, and I'm happy to do so. So let me jump into my presentation, and let's go through. So what I prepared for today was some new metrics that I think are very helpful to identify issues in sensor configuration, with a focus on automotive, but I think these things also happen in security applications or in consumer application. So So as Abdullah already mentioned, my name Uwe Artmann. I'm CTO of Image Engineering. I already got a kind introduction, so there's not much more to add. I'm happy to present here. I have to provide a small disclaimer, just that it's important. So I'm happy here to present on invitation of 10x Engineers and Abdullah. Two things I have to make clear. One thing is just because we operate also as a test lab and neutral third party. That's why I just have to mention that we are not affiliated. So if there's any work done by 10x Engineers and we would test that, it doesn't mean that we are anyhow related to each other, in forms of that we would not leave our neutral position for testing devices. Something that I'm also always asked to give as a disclaimer, when I talk about international standards, let it be ISO, IEEE, VCX, I speak here in my own words on my behalf. I do not represent the organizations, nor do I represent the work groups. So whatever I say about that is my personal opinion, my personal view. So just to have that aside. Just very, very quickly about image engineering. Abdullah already made a kind introduction. So we are a company dedicated to testing and characterizing cameras. We are located in Germany, so it's close to Cologne. We have subsidiaries, US and China, and different distributors within the world, and we are active members of standard committees. That is also just very quickly about where do we come from? Why do I talk about image quality? Well, image engineering started testing image quality on digital cameras already in 1997. So we have quite a history as an independent test lab. So as far as we know, we've been the first independent test lab outside of manufacturing companies dedicated just to digital cameras. So we do that we started with that as a test service in 1997, and then over the years developed a huge variety of different products, test targets, lighting solutions, services, and so on, to help the industry with our products, with our knowledge. We are active members in a variety of sanitization groups. So our goal is always no magic number. So if you use tools, if you use procedures to evaluate your work, so if you tune a camera, if you develop a camera, it doesn't help you if I tell you, yeah, this is a 9 out of 10, and this is a 6 out of whatever. It doesn't really help you because you need to understand where does this number come from? Why did we get to this certain number so that you can plan ahead and see how can I improve on that. So that's why the vast majority of our test services, of our products is based on international standards so that you can clearly see where do these numbers that you might obtain from our software, where does this number come from? How can I interpret this number? So we are at ISO, VCX. VCX Forum is a non-profit organization dedicated to testing mobile phones. That's where it started. It has a protocol for webcams. It starts now activities for HR, for AR, VR activities, and also for security or home security cameras is in the making. So all these, if you're interested, get in touch. I have there my second hat as a head of the standards department in that organization. And then IEEE for P2020, an automotive standard, IEC for security cameras, EMVA for machine vision cameras. So you see in a lot of areas we are active. We produce a variety of products, so test charts, software, measurement devices. So have a look on our website. I'm pretty sure you will find something interesting there. Also from our services, so we provide as a test lab, we are testing cameras throughout all the industry. So companies approach us and ask us to either compare cameras or to help them in the decision-making process, what components to use for their product. And then, so that's what we do as service. And then training is something that we provide, image quality training and consulting wherever is needed for the image quality testing challenges. So if you say, hey, I have these certain aspects of my camera that I need to test, I'm sure we can help on that. Okay. So with that said, as introduction, let's jump into the technical topics. I think as we are engineers or have even engineers in the image engineering, 10x engineers. So I think we are in a community of engineers. So let's talk technical stuff. So there are a couple of challenges when you tune a camera sensor, particularly when you have an HDR sensor commonly used like for automotive. And there are a couple of things that are unique to these sensors or that do not easily show up in standard test protocols that you might use, like taking a picture of a color checker, taking a picture of some slanted edges, and so on. So these standard test protocols. So it's some things you will not find there. So let's have a look what these are. What you see here, one typical problem that you have when you're dealing with HDR cameras, particularly when you have multi-exposure HDR sensors, is that you get these SNR drops or SNR dips. So what happens here is that when we combine 3 exposures into one HDR image. And if I now have a look at the noise over the different light intensities, the illumination, I will find certain spots where I have the transition from one image to another. So typically then I have the transition from the dark region or from the bright region of one image into the dark region of another. And that can look like this. So I have here gray patches from dark to bright, and I have significantly more noise in the bright than I have in the dark, which is counterintuitive to typical sensor behavior, but that is an artifact from HDR. So these are these SNR drops. And you see here also in this plot, This can get worse depending how you configure your sensor. So this is the same sensor, once configured for 120 dB dynamic range, and the other one, the darker, is configured for 144 dB dynamic range. So how is that done? How can we control the dynamic range? Well, the overlap of different exposures is changed. Therefore, we get more, or we don't have that much overlap. So the SNR drops get deeper. So this problem that we see here in the image gets even worse. So configure it. So you have to, when you tune the camera, when you configure the sensor, you have to find a good trade-off between these issues. So how does that look like in an image? So I borrowed here a slide from Orec. She's the lead author for the noise section in the IEEE standard, and she made a publication at the Electronic Imaging. And you see that here from the measurement protocol. So this is here in the sky. It's a bit triggered by to emphasize that, to see that. But you see here in this region, I have more noise than in the other. So in the sky, in the gradient, I suddenly get into noise, or get noisy parts. And this is the SNR dip that you can have. So you have the peaks and then you have these dips. And that's something that is an issue. That's something that that we would like to understand. So I will show you some of the new metrics for that. Another aspect that you have in modern automotive sensors, particularly when you start to tune them, is that you have an issue of like loss of local contrast. So also here I borrowed a sequence from it's like a promo video from Sony, and they show here on the right HDR off. Yeah, we lose completely information what happened at the end of the tunnel, which is, of course, a problem. So that's why we want to have HDR, so that we now can see the end of the tunnel, so what happens on the outside, but we can also see inside of the tunnel. But what we also get from that is that we have a significantly lower local contrast in the tunnel. So if there's a car in front of me, I get a much lower local contrast from that car. And I can, depending on the configuration, even have some areas where I have a complete loss of contrast. And that's something that you can see here on the right in that chart. These are actually images captured with an automotive grade camera with a faulty configuration. So for a certain intensity range, you lose completely the local contrast. And that's something hard to measure, but there's some new metrics for that. Also, another aspect, interesting, or some parts that you can configure or can choose the right sensor for. It's also this flicker challenge. So here's the example. We have a car approaching a tunnel, and on the left there is the traffic sign telling you shouldn't do more than 80 kilometers per hour. So this sign is pulsed, and because of the capturing process, this pulsing causes these flicker artifacts. So that's also something that we can or that we can have some control over by doing different timing settings, configurations. So that's also something that we can config, and that's why we should be able to measure it. Okay, how do we measure that? So the methods that I'm going to present are part of the upcoming IEEE P2020, or have been developed partly in parallel, partly together in that work group, but always with our contribution, so that we can really that we can move that forward. So P2020 standard. So the ballot process for the final document is ongoing right now. So if you depending on the vote on that, it will then go into the formal release process. So I hope that by end of this year or very early next year, we're going to have the final document ready for publication, and then it will be available through the IEEE. Okay, so the IEEE has a protocol to measure noise. So you could get these SNR measurement there. So you use a high contrast test target for that, like shown here. And can get the noise. So the noise section in the P2020 is not a new metric. It's just well, defining existing metrics. So signal to noise ratio is something that isn't new to the industry, but sometimes it's just good to define things well. So that's a task that we had, or that what is done in P2020, or for this section, to define the noise, or how to measure noise. Okay. What is new, or what is a new set of metrics, what I think is the most or very interesting in that document, that are the contrast performance indicators. Under the umbrella of contrast performance indicators, we have the contrast transfer accuracy, and we have the contrast signal to noise, so CTA and CSNR. You find multiple publications on that at the Electronic Imaging Conference over the past years. Note that some of them have been called contrast detection probability. That was the name during the development, but before publication, the group decided to rename that to contrast transfer accuracy, to not confuse that with some form of detection probability, so how good a detection is. Nevertheless, we know that any detection algorithm will require that an object has a certain contrast. So if you want to detect a pedestrian with your car, in your car, you need that the pedestrian forms a certain contrast to the background. Or if you want to detect a traffic sign or a road line, you need to detect that, and that forms a certain contrast. So we can see that here in the lower left in the example. There's some information lost because we have no contrast. It's very hard to define or to distinguish the car from the background, while we have a little more contrast, and then we can distinguish this bike lane from the road surface. So that's why measuring contrast is important, and that's what we want to understand. So we have our camera captures a real life scene, so we measure a contrast, and now we want to compare that to the input contrast. So we compare basically the contrast we have in the image with the contrast that we actually had in the scene. To do that, the standard allows for a spatial recording, which is having targets in the scene, and a temporal recording, which is basically doing step by step, so taking a sweep. I think the spatial recording is more interesting because all kind of influences are part of the measurement. So if there are some dynamic adjustments in the camera, so on, it's included because we provide it actually in the scene. But the temporal recording has a lower requirement on the hardware. So yeah, there's always to find a trade-off for that. So from these contrast performance indicators, what you can get is what you see in the center is like a heat map. So in the center, that's a CTA heat map of a certain of a sample camera. So we were lucky that we got some intentionally misconfigured devices that we could test in the development process of P2020. So here you see on the left there is an issue with a loss of local contrast, and this is how it shows up in the heat map. So the heat map is a very good tool to understand what's going on in my camera, similar to the CSNR plot that we have here on the right. I will go a little bit into more detail how this map is actually created, because I think that is quite important. So what we use for that measurement, and I already said there is the spatial recording, as it is called. So what we use for that is our VLS. So that's the versatile light system. So it's a very flexible solution where you can position high performance, very stable light sources in the scene, equipped with certain test targets, so that you can do a variety of measurements. So with the required software to control the light sources, but also to do the analysis. So what we can provide to the with the camera is then a wide variety of intensity with these targets. So you see that we have so each of these light sources has 6 by 6 or 36 patches. So In total, we have 206, or no, 216 patches with the known luminance that we can then use for our measurement. And we can arrange them in a way that is most flexible for the camera on the test. And then we can put that into our software to get to these maps that you have seen before. But there's also if you read the standard, so the underlying math and the underlying analysis is quite simple. So it is also easy to implement, to understand. It's a very interesting metric. So it's not terribly complicated from the metric. It's more from the what it tells you. So that is the beauty, I think, of CTA and CSNR. So what do we have? So we say we have our target here as an input into the complete camera, into the ISP. And as an input, we just have two patches that have a certain luminance, luminance min and luminance max. That goes into the entire camera, into the ISP, into the processing, and so on. And as a result, we have an image where we don't have a single value, but we get a certain distribution of digital values around these patches. And that's because of noise, that's because of flare, that's because of other things, but we do get the certain distribution there. So now we have the patch data from the target that is known in luminances, while the digital values that we have, while the camera provides us with digital values. So what we do, and that's according to the standard, we measure the OECF, so the optoelectronic conversion function, so the tone curve, and use that to transfer the digital values also into luminances. So that means that we can then compare the luminance contrast that we have in the target with the luminance contrast that the camera measured. So we need that to correct that. So either because the camera works nonlinear or the camera is compended because it wants to compress the HDR into, I don't know, into 20 bits or whatever. So that's why we need these OECF. So now how do we evaluate that? So on the target side, we have, as said, we have these two intensities, L min and L max. That is a certain luminance, and that forms the contrast, the input contrast. And now from our camera, we don't have just a single value. We have these digital values that form a certain distribution. We take the OECF, and now we transfer that into the distribution of luminance. So we can convert digital value to luminance, and now we have two distributions. And now what we want with this contrast formula, we calculate the contrast between these two patches. How is that done? So we take randomly one pixel from the first patch and randomly another pixel from the second patch and calculate the contrast. Then we do it again. One pixel from the dark, one pixel from the bright, calculate contrast, and so on, so on. We do that 1,000 times. So then we get a probability density function of the contrast that we have between these two patches. And that is influenced by the noise, by processing, and so on. So the equation looks more scary than it actually is. Technically, it just tells you we do these probability density function that we see here on the right. So we have a certain distribution, and then we define boundaries. So depending on our application and our detection algorithm, we say, okay, for my application, I need to really well reproduce the contrast because my detection algorithm is very sensitive to that. So I set narrow boundaries, and then the CTA tells me how much of this distribution is within my boundaries and how much is outside. So perfect is 100 because 100% of all pixels I have fall within my boundaries. So 100 is, or 1 is the best possible. 0 would be, is technically, or going lower means more and more pixels are outside. So the probability that this contrast is preserved or the contrast can be detected is reduced. So now we put that into a map. So if we have our map, we see on the x-axis the luminance. So how bright is that? And on the y-axis, what's the contrast? And then in color, we encode CTA. So 1 actually means a high probability, or the probability of 1, that these two patches can be separated. And it's a good performance in intensity and contrast for that scene. And if it's the lower it gets, or towards 0 it gets, we can hardly distinguish that anymore. So to correlate that with a natural scene, for example, so we have here our heat map, just a different color encoding. So let's say we have here, I hope you can see my mouse. So here there is it's a very high contrast, so something bright and dark. So in a medium luminance in average, so this correlates here to this point here. So a very good chance, 100% that the camera can detect this contrast and can preserve that. So we go here in the center of the road. So we have the road marking in contrast to this dark surface of the road. So compared to the other, lower contrast, also pretty bright. So we still can capture that quite well. And then we can have a look here. So this here in the background, 2 bright patches. So they form a low contrast, but are bright. So we are here. That's something where we might still be able to catch that contrast. While we have here some debris or something lying on the road, some parts of a tire. So a very low contrast and low light. So that's where the detection, where the CTA is close to 0, so it's dark blue. So that is something which we can detect with our camera. So that's the idea of CTA, that you can do this kind of analysis. And now have a look at the images. So this is another example of a sensor captured, and now we can have a look at that. So here, we see some dark regions here at the bright end. Yeah, that's saturation. Okay, so here in the brighter end, we still have, it's not completely saturated, but technically it's like running out of bits. So we, in the bright, so just, so there's an issue there. We got these dark ones. Here in the center, everything looks good. Here we start to get a loss of information because it's getting too dark. It's not really separated. Here the noise really kicks in. It's significantly reduced my probability. And if I go here, yeah, I cannot really distinguish the patches anymore. I might see some gradient in here. So that's what also my CTA map tells me. And if I go here, there's complete loss of that. So I can't even see that there is a target, yes or no. But also I have here this effect. I see the embedded dark line. So this exactly shows up now is the effect of loss of low contrast. And this is exactly what shows up here in my lens, in my heat map. So that means this heat map is capable to tell me what happens at a certain region, which if I would just go take that camera and go out on the road and drive, it's not very likely that I can catch this. With this test protocol, I can catch this very small region at which we have a loss of contrast. Another example here, that's a sensor, so sensor A and sensor B. So you see sensor A looks, compare what you have just seen, quite reasonable. And in B, there is something strange going on. So here we have some peaks, interesting distributions. Now, if I have a look at that at the image, I can see again what's going on here. So here is my peak. So that's also a loss of contrast. Here I have a loss I cannot really distinguish that anymore because I just have a few bits left. So if you can see that also with zoom, but there's just a few digital values left. And also here, this is not complete dark. There's just like 2 or 3 digital values left that shall distinguish it. So there is really a loss of information. So you see, this heat map, this CTA heat map is extremely powerful to understand the sensor over a huge variety of contrast and intensities. And so our customers and we ourselves that use that, I think with this measurement, we already saved, I don't know how many thousands of kilometers and hours and days on the road, because a lot of misconfigurations can be found before the sensor goes on the road. And misconfiguration just happens. It's nothing that someone made really a mistake. It's just that they needed to, when they had a new sensor, they needed to learn what's a good setting, what does work for the sensor, and so on. So it's really a great tool when tuning and optimizing the config. Something from that data that we can do as well, and that can, in our experience, it's not standardized, not part of the standard, but it's just a good hint to check the channel ratios. So we have 4 color channels in this case. So we compare like channel 1 and channel 4, which are the 2 greens. So that's a ratio of 1 over all intensity. So that's great because that's green versus green 1 versus green 2. That's supposed to be like that. But then when we compare also red to green or blue to green, we see that this changes very significantly over the intensities. And that's something that is quite critical if color is an important information for you. So that's something which is very interesting to have a look at, particularly if we have more something like this where it really quickly changes. So that you have, it's really, you get into trouble with your with color, with the processing, get colored noise and so on. So that's really a problem. Something we my experience is to really understand the performance of an automotive sensor, you need to go need to measure under different temperatures. So with like here, our climate chamber, that's also a product of us. So you can put the DOT in that and then use the VLS to test. And that's extremely useful. So I have seen good examples where sensor behaved quite well and better as competition at room temperature, but was very sensitive to temperature. So if you then test it at 60-degree ambient, at 80-degree ambient, then you really saw differences. And so that one sensor, so that 2 competing sensors at room temperature, one was clearly better, but at higher temperatures, the other one wasn't as bad as the first one. So that was really, we would have missed that if you wouldn't, or the customer would have missed that if you wouldn't have tested under different temperatures. Okay, so that's the CTA. Something I also addressed at the beginning, what is an issue is some form of flicker. So these Vega light sources that are part of these VLS, they are also they can have a controlled flicker, and what we can do with that is we can provide different kind of flicker frequencies, different duty cycles, and different phase to the camera to see how well does the camera behave under a flickering light source. And they can be terrible. They can be really terrible. So there's a lot of sensors out there that are very, very common to use, and they are very terrible in flicker, so that you get very crazy color artifacts when you have like construction sites where some illumination is, or traffic lights and so on. So it's it's an important aspect to measure. What we use for that is also a part of the P2020 upcoming standard, and that's called MMP. It's modulation mitigation probability. So what we use for that is just imagine you have your camera, you take a video of these flickering light source. What you typically get is that you have some form of change of intensity, either as a like band goes through, or it turns on and off and so on. So what we do is we just have a look at a single pixel. And this pixel we track over the frames. So that's what we have here. So when we track that pixel over the frames, what we will get is a certain distribution. If there would be no flicker at all, I mean, all pixel would just show the temporal noise, a little up and down, but they would stay relatively the same. But when we have this flicker, they will go up and down. So now we can use a similar approach as we have in for the CTA measurement. We now just have a look at the distribution and we define a certain region that is acceptable, which would be like in range of the temporal noise. And then we see here in this upper right, if we have flicker, we form two distributions and most of these distributions outside of my boundaries. And that means I get a low MMP value, while when it's all inside, I get a high MMP value. So that's here in the lower, I have flicker mitigation off. So I get these two intensities, they are outside of my boundaries, so a low MMP. While when I have flicker mitigation turned on, the values are in very similar, in the same intensity, they all fall within my boundary, my set boundaries. So I get a good and a higher score. So also here we can now plot that in a heat map. And it's a lot of data compressed into one into one map. So what we see is here, that's a measurement for one camera and for 10% duty cycle for 10% tolerance interval. So we define the boundaries as 10%, which is quite narrow, but yeah, that means as soon as there is some flicker, we will detect it. And we say for 10% duty cycle, which is kind of a very common, and it's still a bad light source, but a very common light source that we have in automotive. So 10% duty cycle. So now, and the four patches are the four different color channels. Again, on the y-axis, the x-axis, we have our luminance. And on the y-axis, we have now different frequencies that we can check. And then color encoded, yellow means no flicker, and if it goes into the blue, we do have flicker. So what you can see from this example now, like this device at 100 Hertz, it completely suppresses the noise, the flicker, and at 200 as well. But in between, there is flicker. So that's something tricky. So if you see, promotion from a sensor manufacturer and says, look, what great flicker mitigation we have. Yes, for one specific frequency. If you change the frequency slightly, it might be off. And that's something that is at least very good to understand depending on your application. What's also important, that's not what all test labs do. What we do is also to check that over the intensity. Because if you have a multi-exposure sensor, depending on the intensity, you have a different exposure time. The exposure time is a big contributor to the flicker. So that's why we need to test at different intensities. So with that, yeah, we can get here a certain map. So we have the MMP map on the left for 10% duty cycle, and also the MMP map here for 90% duty cycle. So much more yellow. It's less of a problem, but it still is some slight flickering is still going on. So, but you see 10% duty cycle light source is much worse. 90% duty cycle is easier to handle, but it's always still worse to check and to fully understand. So with that said, I thank you very much for listening to me and for that. And of course, I'm happy to take questions or to get into a nice and fruitful discussion. So thank you.
Thank you, Wei. Any questions from the audience? So you can ask.
So can you hear me?
Yes, I can.
Yeah. So really nice to see the work that you just presented and uh, uh, making use of a single system setup and like getting all the things not going out to like do those experiments and viewing all the results in a single from a single setup is like great. It's a great thing to like have. My question was regarding that we have seen the CTA that basically is for the contrast part of the sensor, and then we have seen that the light flicker mitigation is also can also be like one can see the response of the sensor in light flicker mitigation scenarios. So, is there anything, or is it essential to have anything like similar to this for the color accuracy of the sensors? And is there anything that is there for the color accuracy part as well?
Very good question. And yeah, so you're absolutely right. I mean, at the moment, so let me first say no, there is nothing, but it's agreed on the work group or of P2020 to start that as a new project. So you can invite everyone to join P2020. It's an individual membership, so you don't have to be an IEEE member to contribute to the work group. So just as a starting for that. So what is agreed and understood is if you take a picture of a color checker and calculate the delta E. That's not what color detection or what you need for machine vision on color. What we are currently, one idea that we have at Image Engineering, but also within the work group, and we already did some experiments, is what we call color separation probability or spectral separation probability. So what we want to do is we provide two spectra to the device on a test that are very close to each other. And then we check with similar metrics as we had with MMP and with CTA, what's the probability of that device to distinguish these two close spectra. So for that, we need spectrally tunable light sources, which we can provide so that you can or have two basically color stimuli, and you just try to find out, can I distinguish that? So in this direction goes, but at the moment, there is no standard for that.
Yeah, thank you.
You're welcome.
So I have a question.
Mm-hmm.
Thank you for the very nice presentation. So you have mentioned about the contrast, how we are measuring contrast, and see when we use HDR, how the medium intensities their difference actually mitigate, right? So when we actually use the tone mapping curve, there are also some color artifacts happen. Sometimes there is very a slightly sharp slope from dark to light. Sometimes we get to see those color artifacts. Is there any standard, any parameter or anything that actually used to measure? It can tell me what is wrong with the tone mapping, global tone mapping operator, or maybe local tone mapping operator, where we are getting our intensity is not right.
Yeah. So I know these kind of effects. So when, for example, you see that here, this is a single Vega light source that we use, and we can control that in frequency and duty cycle and so on. So depending on the device on a test, you can here it's just intensity, but this can be also quite colorful. So if you have an ISP, you really get color artifacts. Typically, that's an issue about timing, so that the light that in the capture process and then in the merge. That there is a problem. So I can't tell you where exactly to fix that in the ISP because we are from the testing, but I can tell you if you see that behavior on the street, but for example, you're driving somewhere and then in nighttime, and I've seen some examples. So driving at nighttime and then like road markings or some lights, they get into very colorful artifacts while you're driving. That's something that I can definitely tell you can reproduce with these Vega light sources. I mean on the slides you saw my email address. If you send me an email, I'm also happy to show you offline a short video of that example. Maybe that helps you.
Yes, sure. I'll share you with my result as well with the color artifact I'm talking about. Thank you so much.
Okay, yeah, that would be good. Yeah, then I can maybe help better. Yeah.
So we have a question in a chat. It's, how do we measure and separate CTA of an HDR image sensor from contrast deterioration happening due to optics and image pipe algorithms? So, like how to differentiate that the contrast is happening because of the HDR image sensor or due to the algorithms that are implemented in the pipeline? That's like
Yeah, that's a huge challenge and it's maybe you have indicators because that's why we made this. So when you, I mean, as it is a standard, you're free to use your own implementation, of course, but in the way we implement it here with our, that's why we made it very flexible of these light sources. So if you just have it in one measurement, you can't really separate, is it from the lens or is it from the processing? If you just observe, hey, there's a loss in contrast. But what you can do, if you are at least suspicious that might be something in the lens, what you can do, you can rearrange these light sources, position them slightly different, and then rerun the measurement. And if it is consistent, then it's very likely that it is in the ISP. If it changes either its location or disappears, then it's more likely that it's from the lens. So that's so that means in the measurement itself you can't really distinguish that, but you have some indicators, or you can at least run some tests to distinguish from that. Yeah.
okay. So any other question? One or two last questions maybe, since we'll wrap it up.
For your presentation, it was very interesting, useful. I wonder if you could go back to your last slide.
With a flicker.
Yes. Did I understand you correctly? Here is these plots you're now showing us. They are this light luminance dependent is shown here with the, I'm sorry, for one specific luminance point, sensor adjusts itself its luminance. If that's the case, this graph shows the frame rate sweep versus the flicker rate of the source. Is that correct? If not, so I did not understood the purpose. How can the luminance impact of the flicking rate here?
Yeah. So what we do is I try to explain again, and then we can see if that explains the question. So with our what we have is our flickering light source, and on this light source we can control the intensity, the frequency, the duty cycle, and the phase. So that means we put our device in a test in front of that light source or of that setup, and then we capture many images for one combination of this, and then we change the combination. So in this example, this is a map where we change the luminance and we change the frequency. And we need to change the phase to test that. So that means an MMP test typically means that we capture 1,000 and thousands of images to get to this map. And it's a bit misleading, I have to admit here. So this is also interpolated. So it's not that we measure each and every frequency. So we did once a calculation. If we would test just by each individual step, so going from 0 to 500 and going like all one digit up, and then all luminance, we calculated we were in, I don't know, it was outside of my lifetime, that of time that we would need to do the complete test. So that's why we need to pick certain frequencies from that, and then we do the map. For the map, we do the interpolation. But in the measurement, it's a certain number of frequencies that we use, and then cycle through different intensities. Did I answer that, or maybe?
Generally, yes. Could you please answer one more? Was these pictures done with a constant exposition or not? That was the core of my question.
Yeah. So that, I mean, the typical thing that we have, I mean, when we do it here, the cameras are not free running, at least in terms of auto exposure. So it's one. I mean, typically in these kind of multi-exposure images, you don't have one exposure time. You have a combination of many exposure times. So it's one config that is used, and that is one set of exposure time combinations. Yeah.
So if we know the instrumental function of the CCD sensor that can show us how quick the signal can be to be responded by a camera, we can somehow maybe calculate it analytically without testing.
Yes. So if you if you know everything, if it's your own sensor and you know everything about the mitigation process, the timing, and so on, theoretically you could also do this in a simulation. Yes, that's definitely true. But typically, what we have when we test it, or what is a very typical scenario that we have in our test lab, is that like an OEM or a tier one ask us, hey, I need to decide for a project which sensor to use. So then we do these comparisons directly next to each other for different sensors with the setting and the configuration that the sensor manufacturers or the field engineers of that choose. So that we don't play with that, we just test that, and then we need to test it because we don't know all the details. But as a sensor manufacturer, I think yes, if you have all data about timing, you could also run this as a simulation. Yes.
I am not sure about the process, but as an idea, is it possible, for example, to measure this instrumental function using, for example, very quick rate decay lasers, femtosecond, for example, and after that calculate same plots just as a convolution of your pulses with with a given frequency, and this exponential decay response from a sensor. This sounds not very difficult, and it possibly could be a useful instrument for a future
Yeah,
investigations.
I mean, what you then would assume is that you always have a very strict exposure, that you have a very fixed exposure regime. But what the result in the image is also about merging the different frames and so on. So there's more going on also in the ISP. So, but I have to think about it. Yeah, but I think it's might be possible. Yeah.
Thank you.
Thank you.
Yeah, I have one question. These measurements are all about, or the authenticity of these measurements are all about reproducibility, right? You should be able to reproduce these, they should be quantifiable, and the reproduction should be within certain bounds. When you do reproduce these, what generally do you have some bound that, well, the reproduction should be within, say, 3% of what was measured earlier by a different person in a different location?
I mean, typically, ideally, this measurement is all that the person doesn't count. But what is here in terms of configuration is, for example, this tolerance interval. So that is the definition. So it's described in the standard. So it is how you define the boundaries in an ideal world. That's the concept behind it. In an ideal world, you would know your detection algorithm very, very well. So what does my neural network or my detection algorithm need to be able to detect a certain object? And then based on that, you can define the boundaries. That would be in the ideal world. In the reality, what typically is that projects are not synced so well so that the detection team doesn't know about the hardware and so on. So what we in general see, we use very strict boundaries to really see what's going on and what's happening. If so, that means if really like a 80% here or a 60%, if that could still be very well acceptable for your application, even though it's not yellow here. So that really depends on the use case and what the test case is after that. In terms of repeatability, when we want to test, so I mean, we did that within the work group. we did for before we could publish the method, we went under a 3x3 test scheme. So 3 different cameras in 3 different labs, and they have been tested, and then we compared the results. And I don't have the data here, but we got very, very close to each other, even though it was performed in 3 different labs, even 2 different software implementations, and they still came to very, very close results. So that has been tested within the P2020 development work. Yes.
Right. And when you say close results, if you were to quantify these would of course be single percentage differences, I guess, right? Close would be within
yeah,
1 or 2% kind of thing, right?
what we checked for example, here, I mean, if I have these maps, what we checked for, so it's very hard to say, okay, put 2 maps on top of each other and have an average error or something. So what we did is we checked, do we get the same messages? Do we get to the same peaks? Do we get to the same shape? And if we draw some lines, do we get, like, if we say here at 40% Michelson contrast and a certain luminance, do we get to the same CTA values? That's what we checked. I don't have the percentage, but we got very close. I don't have it right, but it is of course not that you would expect it to be like within 1%. Typically, it is fluctuating a bit more because we are checking at noise, and there's a bit more than that. Yeah.
Got it. Thanks.
So thank you, Uwe, for this insightful session. Thank you, everyone, for joining.
Thank you.
Closing the webinar.